Welcome, everyone. My name's Mark, and I'm part of the team at Royal Circuit Solutions and Advanced Assembly. Royal Circuit Solutions is located in beautiful Hollister, California, and our flex shop is in Santa Fe Springs, California. Advanced Assembly is in Aurora, Colorado, and together, our three companies have become the original quick-turn industry leaders. If you need a board faster than you ever thought possible, give us a call. We're routinely known to make boards in a single shift and populate them, including sourcing parts in under 6 hours. If you need some turn times that are just simply unbeatable anywhere else, make sure you reach out and give us a call. The webinar today is going to be recorded. We'll post it within 2 business days at royalcircuits.com/blog. If you'd like to see other webinars that we've done in our Tech Teach Talk Thursday series, visit royalcircuits.com/blog and aapcb.com/blog. If you have any technical inquiries, please feel free to reach out to me directly at mhughes@aapcb.com. As we go through our webinar, please ask any questions that you have in the Q&A box down at the bottom of your screen. All right, today's webinar is on high-speed materials. It is sponsored by Advanced Assembly and Royal Circuit Solutions. And we are very, very lucky to be joined today by Mr. Fred Scheer of Panasonic Corporation. Fred, tell us a little bit about yourself.
Yes, hello everyone. Thank you for having me. Well, I started in this industry back in '74, working at a board shop level, and stayed in the printed circuit manufacturing for 20 years through '94. At that time, I decided to get into technical sales and service, and I've worked for Park Electrochemicals, which is Nalco, Inselectro, and now for the last 6 years, I've been with Panasonic as a business development manager, also supporting technical services for our board fabricators through the efforts of Matrix, our distributor, and our whole group is part of the research and marketing group. At this point, I'm also spearheading the aerospace sector and trying to stay on top of that area as well. So that's me in a nutshell. Been doing it a long time, I guess.
Well, thanks, Fred. We're really fortunate to have you with us today, and I appreciate that you're going to share all of the knowledge that you have. You ready to get going?
I think I am.
All right, let's hit it.
Well, this particular paper or presentation was initially given back in February at the Apex 2020 by a Panasonic colleague. So I took the opportunity to take this presentation, and since it's very general and in its overview, that we can discuss in a overall example of what we see currently, near future, and what we are going to be challenged with in the future with regard to high speed and low loss. Just a couple of data points that had been collected and reported by Cisco Visual Networking. This goes back to 2080, but I think it's still relevant today. If you notice, the internet users by 2020 should be up 62% in comparison to 41% back in 2017. The internet traffic by 2022 will be about 69 gigabytes of internet traffic per month per user, up 20 gigabytes since 2017. If we talk about devices connected by 2022, 3.1 network devices per person, up from 2.1. And as we go through this, internet video, which is a big growth area, will be up from 68% up to 82%. That's the major impact to the system, obviously. Broadband speeds by 2022, 99 megabytes per second, up from 46. And finally, Wi-Fi by 2022, 63 Mbps, speed up from 27. That's a lot of growth and a lot of challenge for all of us. Next slide.
Yeah, that's a lot of video.
It certainly is. It takes a lot of space.
And then we're moving up to 4K, and then 8K's out on the horizon there too. That's just insane. Well, I guess you don't have to download that on your mobile devices, but that's a ton of video. Let's hope it's all family friendly.
What this slide tries to do is position the devices and technologies in their frequency and wavelength in the segments that they occupy. The areas that are highlighted are typically the areas and networks or technologies that we focus on as a group relative to our board fabricators, as well as laminate designers or manufacturers. So as you can see, where we are with regard to the frequencies between 100 megahertz to 1 gig, it's in that that section that we all come in contact with regard to TV broadcasting and electronic keys and so on. And as we work to the right, we'll see the area that will be most challenged with regard to bandwidth and frequencies, working towards higher performing networking systems, routers and servers. Certainly the 5G mobile communication is a large sector. Optical systems, collision avoidance through car radar systems certainly requires a lot of bandwidth and horsepower at that point as well.
Yeah, I mean, 90 gigahertz, I just can't even imagine designing for
exactly
that frequency. That's got to be insane, and some top-notch engineers doing it. All right, we ready for the next one?
Yeah, let's do it.
All right.
The technology trends for printed circuit boards. If we look at that sector as far as routers, servers, and storage devices, we're going to be challenged to improve the products that are presently on the market, to elevate high signal speed through development of improved laminates and prepregs. That would include resins, coppers, and glass. The technology trends will push the densities higher and higher, tighter pitch, higher layer counts, obviously. With higher layer counts, the materials need to be able to withstand multiple thermal excursions. And also because of the higher densities, we're going to require tighter controls of the core thicknesses as well as resin contents. In the wireless sector, it'll be much the same, but I think a heavier emphasis on stability under high temperatures. These types of devices will be under hood or out in the environment, which can be difficult and challenging as far as the net effect on heat and moisture on the materials properties, excuse me, relative to dielectric constant and loss characteristics. Environmentally friendly is kind of a catch-all for the two segments, and we can discuss products that are halogen-free in nature, and if we're talking about copper, possibly arsenic-free type of copper foils. But again, that's always a common theme, and we want to make sure that whatever we're developing for the future systems will have environmental friendly focus as well.
Definitely.
The next slide, please. This is a similar graphic that speaks to both the PCB and the flex printed circuit. Mobile devices. We're talking about, again, higher density and thinner PCBs. So anytime we start to increase the density on an onboard design, flex or otherwise. Certainly the dielectric spacing becomes tighter and the pitch hole to hole it also becomes more stringent. Flexible printed circuits, we've seen them used for replacing antenna, more of a flat configuration or geometry. And of course, flexible copper clad laminates are used either in rigid flex applications and or hybrids where a flex product can be merged or married with a more conventional glass reinforced to make a hybrid multi-layer board, trying to take the advantage of both overall thickness control as well as electrical and thermal performances.
Yeah, I guess one of the nice things about doing the antenna on polyimide material is the material is very uniform. So it must make it, pretty easy from a design standpoint to get good performance out of that. Yeah.
I think what I've learned through the course of this particular growth in our industry is that we're only as good as that connector or that weak link in the total system. So one area always drives the other for improvement, for sure.
All right.
If we can move on, thank you.
Sure.
When we look across the devices that will require advanced PCB materials, there are certain areas that we'd like to acknowledge and possibly even rank. So if we look at the product sectors as depicted on the far left, and the way we've either prioritized or numerized the important attributes, if I may start with the low transmission loss, number one, that's going to come through advances in material resins, glass, spread glass, certainly, and low profile coppers. Thermal stability and its net effect on DK and DF. Certainly, new resin systems will have to be very stable over multiple ranges of heat, both in the high end range as well as sub-zero types of environments. That's maybe more of the aerospace area, but certainly materials have to be able to be compatible across multiple thermal conditions. Dimensional stability, very important. Obviously, when you have product and designs that have tighter pitch and tighter densities, we as a laminator need to apply tighter tolerances. And that's typically going to come in the form of tighter thickness control against the normal IPC standards, as well as resin content control. All these factors, if we're always consuming the entire specification, then the variation in the end product is going to not be satisfactory. So we understand that more and more we're going to have to work to the center of the specs and reduce the amount of variation with regard to, in this case, thickness and resin content. As far as number 4, high heat resistance, with HDI, we're seeing our materials needing to go through multiple lamination cycles. It's not uncommon to see 3 or 4. I've recently seen as many as 7 or 8 lam cycles. So again, the materials, the boards can be designed, but the materials will need to be able to be robust and be able to survive, in this example, multiple lamination cycles.
There aren't that many laminates that are rated for that many cycles, are there?
No, there isn't. I think every laminator that we know of, that we work with, that are competitors, that we all have our go-to materials that we know have the type of robustness that we're looking for. But it's one thing testing materials to multiple thermal excursions, but it's the peripheral processes that also contribute to the success, the drilling and the plating and the oxide treatment. You can have a material that's extremely thermally robust, but if the components of putting, designing and fabricating the circuit patterns, they need to be as capable as well. And that's where we like to help wherever we can, at the fabrication level, and try to provide the most robust condition that we can, given the environment that we're working in.
Okay.
Number 5, high insulation reliability. I relate that more to being able to survive extremes in ranges and moisture absorption, and the possible net effect on electrical performance as well as mechanical strength.
So a quick question. Panasonic started to source glass and copper from non-Japanese vendors. Is that correct?
Yes, that is correct.
So how do you verify reliability and material properties of being consistent across multiple plants?
Well, we do a very thorough job, as all laminators do, with pre-qualification, and there are standards within our industry and our sector that must apply. So it's doing a thorough research on the raw materials, the process, and the availability of the raw material strain. So it's a quality process, and it really needs to be adhered to. And I think we have a slide coming up that speaks a little bit more directly to your question.
Okay.
We can move on. I'm sorry, one back. There we go. I'm not going to get into all the physics here, but basically, signal and transmission loss is a sum of the conductor and the dielectric contribution or loss. So from a conductor, the copper foil is the driver, and so we're going to be driving lower profile to the point of no profile, profile-free conductor or copper foil. The contribution to loss from the material side will be certainly something that the laminator will be driving relative to new formulations in resin systems, as well as defining the next level of low decay fabric that will be part of our high performance material sets. The next page, please. There we go. The pyramid, if you will, we have ranges of mid-loss that occupy space between 5 and 10 gigabyte, low loss 10 to 25, ultra low 25 to 56, and the next generation will have to play in that 112 gigabyte sector. Those are high-end servers, routers, optical network switches. Future high-speed materials, ultra-low loss materials for ICT, they're going to require certainly the lower transmission loss, suitable for higher layer count. I think in that area, I think it's important that we understand how well we can control the resin rheology properties, that we're going to need to be able to manage the fill and flow characteristics on these higher layer counts. They're not necessarily because the copper thicknesses are getting thicker. It's about uniformity of copper plating on subs, as well as copper densities and distribution, on how we can make sure that the resin from the prepreg does a thorough job in filling and encapsulating the copper trace features internally. There's one thing developing glass and resin systems, but it has to be manufacturable as well. Can you drill it? Can you plate it? Will it survive multiple lamination cycles? And as boards get thicker and more dense, they need to have lead-free reflow compatibility. Boards, as I'm preaching to the choir here, but boards go through numerous reflow exposures. And so the package needs to be able to withstand the kinds of z-axis expansion that boards will see under these multiple thermal excursions. Lastly, on this slide, I kind of like the arrow swoosh because it does kind of encapsulate the importance of looking at the total system and not just hoping to get your improvements or benefits from one area of the material package. Resin systems, they're fixed. Once our technologists have developed that low loss resin with the filler content and the resin content and what goes into formulation, that is a fixed entity. Now we're tasked to go out and find quality glass cloth. Low decay glass is going to be a standard for improving high speed, low loss designs. Copper foil is certainly getting a lot of attention. Copper foil, certainly low profile, needs to be in order to be able to keep signal loss, insertion loss at a reduced level. And once we establish copper foil and its profile, lower profile, there is a process that we're familiar with it's called oxide treatment, if you will. It's an adhesion promoting process. And in days gone by, we were under the school of thought that rougher was better from a laminate or prepreg adhesion. But we know that if we allow the adhesion promoting process to roughen up the copper, we've lost all the benefits of seeking out lower profile copper. So the industry is rapidly working and developing newer adhesion promoting systems, getting to the point where we're nearly at no topography after oxide treatment.
That's pretty crazy. Okay, so currently the adhesion of copper to epoxy laminate is on the order of, like, I don't know, 1 to 10 plies, right, or whatever the unit is, newtons per linear inch. So we're going down from that now, because I mean that's the adhesion level of Scotch tape, and it's going to get worse, you're saying?
Yeah, I think we can't do this in a vacuum relative to, we are working with the chemical suppliers as well as the copper foil suppliers, because the copper foil certainly has two sides. We can manage and control the treatment side that we specify from the copper foil supplier. And the drum side, or the shiny side, that the PWB manufacturer has to create circuitry on, that's the area that we need support and visibility on where we're going with that. So to answer your question, Mark, we are probably neutral or minus neutral relative to where we're going for bond strength. The older systems, when you say epoxies tend to stick to everything. They're not really a problem. It's the high functionality, high speed, low loss materials that are not necessarily an epoxy. They could be an epoxy blend, but now we're relying on less mechanical adhesion properties and more of a compatibility from a chemical standpoint, where we have silane coupling agents or different treatments from different chemical suppliers that have an affinity for improving the wet out of the high speed, low loss resin systems to itself. So that's really where our focus needs to be.
Interesting. All right. Well, thank you.
We talked a lot about low decay fabric, and I think it's going to be the standard in the future. And it goes back to that swoosh arrow. We can get a lot of benefit on finding and using lower DKDF fabric. And what I wanted to illustrate on this particular slide is the electrical properties for both the E-glass and the low decay glass in its raw state. As you can see, the E-glass at decay values at 2 and 10 gigahertz, they're roughly in that 6.6 and down to 6.4 at 10 gig. But if you shift over and look at the net effect of specifying a low decay fabric, you get a significant drop in DK and DF. So by simply using and developing and improving, finding lower dielectric constant fabric, that the resin system can stay mature for a longer period of time, where we can get our electrical performance enhancements, speed and loss through the use of the glass reinforcement, the lower decay properties. The second part of this table simply compares some of the mechanical features of both the E-glass and the low decay fabric. They're very similar in that particular example. Any questions there, Mark?
No, I think I'm good. Thanks.
Continue on the topic of glass cloth and its contribution to transmission loss. In this particular example, our test vehicle uses a 1,000 millimeter length circuit, 50 ohm target, 1 ounce copper using HVLP copper. The resin content on the dielectric for this particular TV is 1078 glass with a resin content between 64 and 67%. And that is the core. And then the bonding ply is also a 1070 glass 2-ply. So we need to keep those things constant as we do these types of measurements. What we're seeing in the graph here, if we're comparing two different resin systems, an ultra low loss and a standard low loss, and simply switching out the glass reinforcement and measuring its loss in dB over frequency. As you can see, our ultra low loss material with low decay glass, the red line, has less loss, if you will. And if we combine a high performance, ultra low loss resin system with an E-glass and compare that to a lower performing resin system, more of a standard low loss with low decay glass, you virtually get the same net effect. As you can see, the lines are on top of each other there. And as a reference point, the low loss product, or MEG 6, if you will, in this case, with E-glass, has quite a separation between the high performing low decay fabric.
So without getting into any exact dollar figures, what am I looking at a cost adder to get myself that extra 10 or 11 decibels of performance?
Well, at this point, it certainly is a availability and marketing. I could speak to the fact that we are incentivizing designers as well as fabricators to have price points very close in nature between the low decay glass and the standard E-glass. So they're probably within 5 or 10%. Kind of out of my bailiwick of knowledge.
Of course. Yeah, and I never want to pin anybody down to exact dollar figures on a presentation like this. It's just it's too application specific. What about processing differences or failures or yields between those two?
Yeah. Great question. So far, I could tell you that processing a product with low decay fabric versus a standard E-glass is virtually transparent to scaling factors or to the drillability. There might be an initial difference in the dimensional stability, but once you've characterized the fabric by the glass type, it's very repeatable. So they're virtually drop-ins and lamination. There's no difference there. There are some limitations relative to glass style availability from E-glass to DK glass, but maybe only one or maybe two glass fabrics that may not be interchangeable between one glass type or the other. But you will find that the industry has a vast building block selection across multiple glass thicknesses and resin contents.
Okay, and they use the same resin on each of these?
Yes, exactly. So if you're concerned with qualification or UL, once you have a particular resin system qualified, if you happen to have a design or a drawing that requires the low TK fabric, you're already in. You're qualified. So there isn't anything special or different from a performance standpoint relative to the things that we typically are concerned about.
Okay, we do have one other
Yes.
quick question. Go ahead.
A quick clarification. I don't really see fabricators making the decision to run low DK versus E-glass on their own. Either it's on the drawing from the designer, or the fabricator may see that there could be a benefit for making a change, either to a low DK fabric or back to an E-glass. So there's some conversation that is typically part of that process.
Is there a specific frequency at which it becomes interesting or it becomes useful?
There probably is, but off the top of my head, I really don't have that line of delineation. But I'd be very happy to follow up on that question. We have data that I'm sure would support an answer for that.
Okay, and then one last question before we move on. If somebody's using these for, let's call it space applications or some high vacuum experiment, where do they find information about outgassing characteristics?
Very good. I happen to be the guy that does all the outgas testing, facilitating at least. And we have outgas data for each one of our resin systems. And all the designer or OEM or fabricator needs to do is send me, or frankly, anybody within Panasonic that they're in contact with, and ask for outgas report per the specification, and we will send it to you post haste.
Oh, cool. Okay. Well, thanks. Let's keep rolling then, yeah?
Yeah. This is just a continuation of the discussion on copper foil roughness. RTF, it's a great product. It's been around for quite a while, and it did a lot for our industry relative to promoting improved adhesion and processability. But because of signal integrity issues, RTF is going to be taking less of a role in future designs because of its roughness. Then the HVLP, the RZ factor of 2.3, that's presently a very prominent foil specified right now in our industry. And most of us laminators are working on the next level of low profile copper, and that would be in this case with the naming, if you will, would be HVLP 2, and there is an HVLP 3 out there coming. So this crude diagram, if you will, just tries to illustrate the rougher the surface, the higher the resistance and the greater the loss. And so if we can develop copper trace on low to no profile copper foil, the path is shorter and the loss will be less. So copper profile is one of the main contributors to transmission loss.
So how are you guys making this HVLP2 and HVLP3? Is this rolled and annealed or electrodeposited? I would assume electro and then post treated, or how do you do it?
Yeah, that is a process that is managed by the copper foil supplier that we are partnering with. So we have criteria going in, and they are certainly pulled in multiple directions by multiple laminators. and there's some adaptation of industry standards relative to roughness. So copper foil suppliers, they understand that their process setup would generate a particular copper foil profile. The drum side is typically always going to be very smooth by the nature of the highly polished stainless steel drum or titanium. But the side that's exposed to the cathode, or I should say the anode, that's where copper grain refiners and how you control the actual rectification or current, which creates the grain structure, the nodulation. That is something that is a science that is very well controlled, and will be different process setups to generate different roughness finishes, if you will.
Interesting. Yeah, I can't even imagine how smooth this stuff must be.
Mark, I think there are opportunities to do standalone meetings like this on just copper and just glass, because there's so much behind what goes into defining and developing those components of the total system, that it probably deserves its own time. There's a lot that goes into that.
I imagine. Fascinating stuff.
Copper foil roughness again, the skin effect. We hear people mention this on occasion. And what I would like to just reference here is that the higher the frequency, the more significant impact that it has on skin effect and transmission loss. So I've highlighted the 10 gigahertz at the bottom, and you can see at 10 gig, the skin effect is very minimal. The signal is just traveling along the surface. At the lower frequencies, the skin effect would be deeper into the trace as well.
And for those of you out there who might not remember skin effect from your physics classes, anytime you have an alternating current, as the frequency goes up, you start establishing eddy currents in the body of the conductor. So that increases the resistance dramatically. So all of your current, it ends up moving along the surface, the very, very outer surfaces of the conductor. And you don't get much in the middle just because you've got high resistance due to those eddy currents. So that's your skin effect.
Awesome, Mark. That's
yeah. Good. All right. So ready to move on?
I am.
Okay, sir.
Well, we're still on the topic of copper foil, but it is important. This particular test vehicle, we're using our ultra low loss material, Matron 7, plus the low decay fabric. We're keeping the resin and the glass constant for this test. As you can see, the TV is made up with half-ounce copper, 1078 prepreg in the core, as well as the bonding ply. For the purpose of this particular experiment, the copper trace or circuitry has no surface treatment. We wanted to remove any element or contribution from a copper surface treatment. You can get away with this in a lab making test vehicles, but you can't get away with it in real life, not running a treatment, if you will. So again, we've kept the resin system a constant. We've kept the glass reinforcement a constant. All we've done is manipulate the copper foil type. And as you can see, the green line on the top represents the HVLP2. Then the red, accordingly, is the slightly higher profile copper. And then the RTF down at the bottom. So this is just a little graphical representation of what the contribution is of the copper foil roughness, giving your test vehicle, your impedance requirements, and your resin system constant. So this does give you a good separation of what occurs basically on your signal integrity and its effect from the copper foil roughness.
That's pretty crazy. What about etch factors on these very, very low profile?
Well, I think that's also a very good question because what happens here is because there's less tooth or embedded structure in the substrate during the etching process, you're probably going to find a faster etch rate. So that needs to be accounted for relative to the types of uh, engineering planning documents on etch factors by copper, not necessarily just copper thickness, but also copper type. A copper foil that has a larger nodule profile or heavier tooth, you may have to do a little bit of what I would call over etching or undermining to get that copper out of the substrate. So the less profile, I typically find that the etch rates are higher, faster through the system, and your capability of tighter line widths is also improved.
Yeah, I was going to say this should be able to at least some degree improve your trace and space specifications.
But at this point, I think I need to inject that there's no free lunch here. When you start to work with smoother and smoother copper foil on your core material or the substrate you're making your inner layer with, there's going to be an experience shift or challenge on getting dry film adhesion um, to be as good as it needs to be to retain the kind of print and etch yields that you're accustomed to. So working very closely with your dry film supplier as well as your equipment and your chemistry, your pre-cleaning chemistry partners. That hey, what I'm getting to a point where I'm using a lot of ultra low, very thin profile copper foil. Let's review my process and make sure that I can do this without losing yield points. So I think that's important.
Yeah,
RTF is very forgiving, but the smoother you get on the surface, the more difficult you're going to find with dry film adhesion.
So much to think about. So much to think about.
This is an illustration, if you will, of the net effect of different types of interlayer treatment and how it affects dB loss over frequency as well. The upper portions of the chart, we have no treatment, and these are actual chemical suppliers A, B, and C, but we just didn't list them. But as you can see, the non-roughened treatments, both A, B, and C, as well as the no treatment, they are very close, in a close band, if you will, with regard to loss characteristics, as you compare it to the old standard treatment, which is the brown oxide, if you will. The point here is that this development with the chemical suppliers is getting us to a point where signal integrity is getting closer and closer to no treatment. But again, we have to, be cognizant of the fact that with this lower profile and lower loss surface, we have to, have a special attention on what are we doing for peel strength, bond strength, mechanical integrity, thermal integrity of the total package in the z-axis through reflow or other thermal excursion.
Are there any effects on vias with the two, rough, smooth or versus roughened copper?
Boy, I don't think so, but I'd probably like to think about that. It sounds like a very basic question, but I don't think there's a net effect difference. It depends if it's on a surface of the plated sub, possibly. If it's a foil lamination versus a cap core construction, possibly. If you're talking about pad adhesion, certainly I think there is a degree of change or difference.
I don't know. I was just curious. All right, let's keep rolling. We're
getting down to the end here.
Yeah.
This is a slide I just had to throw in there because given the direction that we're going, using an ultra low loss product, um, and as this example will illustrate where we are and where we're going, at 12 gigahertz, looking at copper foils and glass, you can see where our data would indicate we are centered. This is you have to take into consideration the resin content. In this case, it was a 2116 55%. But as we move forward with the same settings, if you will, we anticipate that.
Oh, sorry.
Yeah, we anticipate that we will be looking at DF in that 0.0015 and DK at 3.2. I think it's very important that everyone understands, and I think most people do, that when we look at diagrams and graphs and scales, that resin to glass ratio relative to measuring electrical performance is key. Because as you change that relationship between how much resin do I have on the fabric and what kind of fabric is it, the output will be different. So what laminators like ourselves will show you, and we'll have clear footnotes that these values are based on this reference point relative to the test vehicle that has been applied.
All right.
I think if we can skip the next two, we'll be fine. In fact, if we could even get to the last slide, I think it embodies what we've been talking about for the most part of this last 45 minutes. Going forward, the 5G world, millimeter wave, it's broken record. We're going to be looking for lower DK and DF resin systems, smoother copper, both at the raw material stage as well as what we're doing with our partners who are developing the interlayer adhesion promoters, working towards no texture or no topography. Dimensional stability is going to be highly important. Higher layer counts, tighter pitch devices. We don't have the kind of tolerance budget that we had a year or 2 years ago. So things are going to, not just the processing, but the material repeatability is going to be key relative to dimensional stability. We've embraced as an industry spread glass, and we all know it's part of the material set, but certainly the spread glass has given us a lot of benefit that we don't talk a lot about, and that is the signal integrity over the surface of a substrate. The resin to glass ratio or presence is more equal, so you don't get the interruption of resin rich to glass rich locations across a field. So that's going to be a factor of our glass selection and style. Low CTE, again, keeping the amount of movement in check relative to the z-axis. We want to maintain interconnect integrity through the plated through hole, vias, structure, as well as surface. So low CTE is going to be a factor. Higher TG kind of goes hand in hand with low CTE. Thermal performance and stability. I think that mostly speaks to that once the product is in the field functioning, that it needs to have repeatable, constant performance from the electrical standpoint over the different ranges of exposure that the product may be seeing in the field or even embedded in systems. And again, moisture absorption is always something that's lurking, and our materials need to be less moisture absorbing or more robust against moisture absorption, so we don't have corrosion issues and or concerns with how moisture affects signal integrity. And Mark, with that, I think I ran through all the slides.
Hey, I Certainly appreciate it. Let me go back to the very beginning here and get your email up. We're doing a Acrobat instead of PowerPoint today. So if you have any further questions, now's a good time to ask them. You can also email fred.scheer, that's fred.scheer at us.panasonic.com for specific questions regarding pretty much anything on the material properties or even tilted toward test characteristics, including outgassing. Shoot them an email. Or if you want to not worry about any of that, you can contact your sales representative, tell them what your needs are, and then our stack up engineers do all the material science sourcing for you. So if you have any questions, now's a good time to ask them. We covered quite a few of them as the presentation was underway. If you would like a copy of this presentation, we are going to have that available at royalcircuits.com/blog in video format and PDF of the slides within 2 business days. The question is, and I don't know that I'm equipped to answer it for you, which Panasonic materials does Royal Circuits normally stock? Do you happen to know that?
Well, I know that I've had opportunities to work with the folks in Northern California on Megtron 6. And down in Santa Fe Springs, they have started to use or qualified our Philios Flex material.
Okay, and there might be more than that, Larry, and Panasonic is just one of our suppliers. So the best way to do it is get in touch with our stack up engineers. They'll let you know what we have on hand, because it can be a huge cost adder to your product. If it's not something that we normally stock, we either have to go out and buy a bunch of it, or we have to wait a long time. You'll get a 1-month lead time on getting a hold of enough to make 1 or 2 boards. So that's a great question, but I'm afraid I can't answer that for you. Any other questions? Please ask them now. And I will, while we wait to see if we get any more, I would like to remind everyone that we can do custom webinars for your engineering team. Just get in contact with sales@aapcb.com or sales@royalcircuits.com. These webinars are free and we schedule them around you. All right, it looks like that's about it then. So I would like to thank everybody for your time. This webinar has been recorded and will be available at royalcircuits.com/blog. Any final thoughts?
Just want to thank you again. I appreciate the time.
All right, this was the last webinar in our Tech Talk Teach Thursday weekly series. We're going to take a break for a few weeks, and then we're going to come back with some other topics. One of the more exciting ones, we're going to talk with Tom Househair of PCBlibraries.com about some new software that's coming out that will make your job as an electrical engineer easier with some custom footprint and 3D models. So thanks, everyone. Have a wonderful, wonderful week. And keep an eye out for our emails. We'll let you know when we start this up again. And contact with any questions, sales@royalcircuits.com or sales@aapcb.com. All right, that's it. We'll see you around.
Thank you, Mark.
Thank you. Bye.